Okay, so this talk is called Identity Testing and Lower Bound for read-K Oblivious ABPs. And we've seen read-once oblivious ABPs many times in this workshop. I will define it once again because I have this amazing picture to show you of a read-once oblivious ABP. It's, you do not seem impressed enough, but yeah, so this is what it is. It's a layered graph. It's a directed layer graph. There's a source node, S, and a sink node, T. And each path from S to T, which is just, we think of it as computing the multiplication of the edge label. Each edge is labeled by a polynomial. And what the polynomial the program computes is just the sum over all path, over all S to T path of these, of the polynomial computed by the path. And it is read once and oblivious in the sense that every layer contains at most one variable in some order. Let's not commit to the order for now. And each variable labels at most one layer. So, so this is the model. We probably know it. Yeah, so I've noticed we've been calling it ROABP, but there's two O's, right? There's once and there's oblivious. And it's important, because the word oblivious is important, even though we tend to omit it. I don't know why we've settled on one O. Maybe Michael has some convincing answer.
I blame the bullying people.
Okay, yeah, it's good that we have someone else to blame. But yeah, but it's, I mean, it's not, the word oblivious will be important. And
put 2 over the O and it will be flashing.
Oh, right, that's an amazing suggestion. We should, yeah. So that's a read once oblivious ABP. We associate the main complexity measure we care about is the width, because the length is almost, and I mean, if the polynomial depends on all the variables, the length is just the number of variables. So, but we mainly care about the width, which is just the maximum number of vertices in a layer. And equivalent way to think about it, which will also be important, is just F is the 1-1 entry of matrix multiplication. So MI is a matrix that corresponds to the ith layer. We've seen this as well, but a recurring theme is this workshop is defining things over and over again. So why?
In your picture, the polynomials on the edges are all linear. Is that what you require?
Yeah, this is okay. This is a good point. They don't. Yeah, I can also allow low-degree univariate polynomials. For this talk, let's assume everything is multilinear because we will have one less parameter to account for. But certainly, everything makes sense even when you allow low-degree univariates. This is a good comment. Yeah, so we have this iterated matrix multiplication. MI is a matrix of univariate polynomial, and let's assume they're all linear polynomial in X pi I, so there is some permutation on the variable which determines the order. And yeah, you just multiply everything together and take the 1-1 entry. This is what this program computes. All right. The good news about read once oblivious ABP is that we know many things by now. So just a reminder that, again, things we've seen, Nissan proved an exponential lower bound for this model. When he introduced them, they came for free with an exponential lower bound. There's a polynomial time white box algorithm due to Raz and Shpilka. There is a sequence of papers on quasi-polynomial size heating set. So in the black box, we know quasi-polynomial time, which is not polynomial time, but it's not far. So this is the work of Michael and Amir, and then with Ramprasad, and then Agarwal, Gurjar, Korwar, and then Saxena that gave quasi-polynomial, and you don't even have to know the order. In the Boolean case, for example, there's Nissan's generator that Parikshi talked about. It's very important when you design a PRG for a read-once Boolean branching program, oblivious Boolean branching program, you actually know the order. I mean, you can assume the order is first you read x1, then you read x2, and then xn. Here, it remains quasi-poly even when you don't know the order. And we have seen other talks in this workshop about extensions of this model. So we've seen a talk about white box and black box PIT for sums of read-once oblivious ABPs and polynomial time algorithm when the width is bounded. So that's great. That's good news. And in this talk, we'll talk about a natural extension, which is read-k oblivious ABPs. Yeah, there is a definition, but I can assume you could guess the definition, right? So it's still oblivious. We still have that every layer contains one variable. But now every variable occurs in at most k different layers. And yeah, you can just assume it occurs in exactly k different layers. It doesn't really matter because you can add just dummy layers. And yeah, that seems like a natural extension. And let's think of k as some constant because, well, because all the bounds will be meaningless when k is a bit larger. But we can think of k as a small constant. So, so that's the model. All right, so let's think for a second. What does this model extend? What does it capture? So it's not hard to see when you think about it for a minute or for less that sum of k read-once ABP is just special case of read k, because yeah, you can sort of connect it in a way that will be read k. So every sum is a special case, and this model was studied by Arpita gave this talk, right, about PIT for this model. It is also a generalization of the model of bounded read formula. So if you have a read k formula and you do the natural transformation into an ABP, what you get is you get an ABP where every variable appears in at most k edges. And then it's not, again, too hard to see that you can sort of expand it by a little bit and get a read k oblivious ABPs. So this model was studied by, there's a paper of Matt Anderson and Dieter van Melkbeek and Ilya Volkovich, and they gave PIT for read k formulas, read k multilinear formulas, I believe. And there's also a Boolean analog for this model, so a read k Boolean branching program, which was interesting for some people a while ago. Yeah, maybe we should spend a moment on it. So read-k Boolean branching programs, we actually have lower bounds. We have exponential lower bounds. So there's this, yeah, again, when k is constant, this is exponential in n. And this holds even for, so you know, in Boolean, you can define a non-deterministic branching program or a randomized thing. And these papers give really good lower bounds on this model. But in the PRG front, which is sort of the natural analog of PIT, the situation is very different. So the best thing is this paper by Impagliazzo, Mecca, and Zuckerman. So they give PRG whose string length is square root s if you have a branching program of size s. So in some sense, this is very general. This is not only for read k. This is for any branching program. So it is very general. On the other hand, it's meaningful only when s is less than n squared. So this is a bit disappointing. And it's also, as I said, it's very general, which is good, but it doesn't exploit in any sense. I mean, you could think that read2 branching program, for example, would be very weak. So you could exploit some weakness in order to design a PRG, but we cannot do it. I mean, we have pretty good things for read-once and nothing for read-2. I mean, except this very general thing. So, in PRG terms, this model is not very well understood in the Boolean world. Yeah, so what I will talk about today, what are the results for read k oblivious ABPs. So we can show a lower bound, which is okay, just slightly worse than what we know for Boolean things. So we can give a very simple polynomial. It has a multilinear depth-tree circuits, but still, if you want to compute it with a read k oblivious ABPs, the width must be exponential in n over k to the k. And in a PIT algorithm, we can give something which is non-trivial. It is subexponential, again, barely subexponential. When k is, so yeah, the running time is exponential in n to the something which is smaller than 1, which is, yeah, okay. And it is also, I've called it white box, but you also actually need, what you need to know is the order in which the variables are read. So are we calling it gray box now? I don't know what is the official term, but I like the word gray box. So it's a gray box algorithm. Yeah, so, I mean, yeah, you only need to know the order, not the actual wiring of the circuits. That is the point. Yes, so I will talk a little bit about the proof. First, I want to provide a reminder for a useful thing we've seen. I don't know if it was, I mean, it was defined, but I don't know whether we use the exact same definitions or same notations. So I want to define the evaluation dimension of a polynomial with respect to some partition of the variables. So f is some polynomial, and s is some subset of the variables. And the evaluation dimension of f with respect to this partition, f and s bar, is the dimension of the linear space that you get by fixing all the variables in S to whatever you want, and then looking at the span of this polynomial. And then you take the dimension. So I think in Michael's talk, he restricted his attention to, I mean, you can restrict XS to, it stopped working? No, it works. Restrict the evaluation to a specific subset, but I mean, let's allow ourselves to fix the variables in S to anything from the field, any values from the field. And yeah, so, okay, I will just reiterate what I said. You fix the variables in S to whatever you like. You look at the span, you compute the dimension. That's the evaluation dimension of F. And why is it useful? Because it exactly capturizes the read-once oblivious ABP's complexity of F. So what Nissan proved, he didn't use these terms, but what you can prove is that F has a read-once oblivious ABPs of width W in the variable order x1, you first read x1 and then x2 up to xn, if and only if whenever you take a prefix and you compute the evaluation dimension with respect to that partition, so this is the evaluation dimension with respect to 1 through I, and then I plus 1 through n, if and only if this dimension is at most W. Is it, yeah, this is also, I mean, when this was mentioned in the bootcamp, we used the term that Nissan's partial derivative matrix. This is basically the same if you have to assume the field is large enough, but let's ignore this. These are just the same, it's the same number, right? So it's, so it must be true.
F is homogeneous, right?
No, why? F is, yeah. Yeah, you need to show that one spans the other, and for that you need enough evaluation point, because there's some interpolation going on there. So it's the same measure, yet, okay, somehow it feels, for what I'm about to show, it would be a little more natural, I think, to argue with regards to evaluation, as opposed to with regards to coefficients. It will make the arguments slightly simpler. Yeah, so that's the evaluation dimension. And let's do a warm-up case. Let's imagine the simplest case we can think of read k, which is read 2. And let's further assume that you just pass over the variables twice in the same order. So I call it a two-pass ABP. You first read x1 and x2, and then up to xn, and then you read again x1 and x2, and move along up to xn. And I've expanded the thing a bit. I just wrote f as a multiplication of matrices. So we have m, there are many indexes in this expression, but you have the first m of x1, and then the first m of x2, up to the first m of xn, and then the second m of x1, and so on, and you end up taking the 1, 1 entry of this thing. And let's think how the evaluation dimension of such a thing can look like. So you fix x1 to some field element, alpha 1, and now what you get is the following expression, right? This is f restricted to x1 equals alpha 1 is this expression, right? I mean, instead of m, you have some constant matrix, n, which only depends on alpha 1, and then you have n2, and the rest stays the same, right? That's it. Now let's think what happens when you further fix x2 to alpha 2. So again, you have these constant matrices. N1 is a matrix of field elements. It depends on alpha 1 and alpha 2, but it's just W cross W matrix of field elements. And again, now you multiply by the matrix of x3 and xn and so on, and then n2, alpha 1, alpha 2. Okay, we've seen what happens for 1 and 2. We can generalize what happens when you fix x1 to xi to alpha 1 to alpha I. Again, you get this expression when you have some matrix of constant that multiplies the matrix of xi plus 1 to xn, and another matrix of constant that multiplies the matrix of xi plus 1 to xn, the second time they are read. So what do you get? That any polynomial in this subspace, in the subspace of f when you restrict x1 to xi, is just completely determined by these matrices, right? When any polynomial can be written like this. These matrices are W cross W. So they have W squared entries. Right? So the maximum dimension this space can have is W to the fourth, right? Because you can describe to me any element in this subspace by telling me the entries of these matrices, N1 and N2. So the eval dimension of F with respect to the partition 1 through I and I plus 1 through N is at most W to the fourth. Is that clear? Should I say it again? That is the hardest part, I guess, in this talk. And everything else will be easy. But this is also easy. So should I say again? Is there anything unclear? I guess you're all just too tired to. Because there are two matrices, and each one have W squared entries. They are W cross W. So you just, yeah. So I assumed for this talk that everything is multilinear, that things are multilinear. It can be, I mean, what? Yeah, I assume each layer is linear, contain linear polynomials in xi. This assumption is not necessary, but otherwise I will have to keep carry this degree parameter that I don't want to. Okay, maybe I should use the blackboard for these things. I have too many things in my hands. Okay, so yeah, so you want to write. The claim was that if G is any polynomial that we get from F by restricting x1 to xi to alpha 1 to alpha I, then G is some matrix of constants, I call it N1, times mi plus 1 through mn times n2 mi plus 1 mn. Oh, this is not the same m, so m prime. Right, this is just what's written there, but without the variables because we know it. So, so I want to show this dimension is small, so let's find a basis for this dimension, for this subspace. So n1 and n2, this is a subspace of polynomial, n1 and m2 are in F W cross W. And for this subspace, I know I have W squared dimension, so I can pick a basis B1 through BW squared. And then what I get is that G is, I want to write N1 and N2 as sum of constants, sum of scalars times these matrices which span FW to the W. So what I'm going to write is sum alpha I bi mi plus 1 mn times sum beta I bi mi plus 1 to mn, and then you can just expand this product, right? So what you get is sum of things of the form, beta j m1 mn times beta k, bk, I'm sorry. Sum over j and k in W squared. Right? So these matrices span the entire dimension of polynomial. So how many choices, how many elements of like this do I have? Well, I need to pick j from 1 to W squared, and I need to pick k from 1 to W squared. I see people nodding, so I guess it's cool. Okay, so the bottom line of this discussion is that we had an equivalence, right? Evaluation dimension was something that characterizes read-once ABP. So if the evaluation dimension is small, F actually has a small, Sun tells us how to construct this small read-once ABP. So, the bottom line is that reading twice in the same order is not really much more powerful than reading once. It can only be polynomially weaker and with complexity. So that's great, right? Because for read once, if you reduce to read once, we know how to do things. We know how to prove lower bounds and how to do PIT. And it generalizes pretty easily to something that I called k-pass. So now you traverse over the variables k times, but each time you do it in the same order. And then you just run the same argument, and you get that for every prefix, x1 through xi, the evaluation dimension is at most W squared to the k. And again, when you think of k as constant, that means that reading k times in the same order is not much more powerful than just reading once. Yeah, so again, F is computed by a read-once ABP of small width, which you get for free these lower bounds and quasi-poly black box PIT for this model of k-pass ABPs. Okay, so we solved an easy case. Let's think of the next case, which is non-trivial. So you pass 2 times over the variable, but you do it in different order. And what you can show this is not captured by a read-once ABP. You can prove that it is exponentially more powerful than read-once ABPs. And you can even prove it exponentially more powerful than sums of read-once ABPs. So you cannot trivially use previous construction in order to make this work. So this paper of Vinit, Neeraj, and Chandan that shows something that is sum of two read-once ABPs, which is exponentially more powerful than one read-once ABP, and we show some simple polynomial that you can compute in 2 passes, but it requires large width when you compute it as sums. Okay, so I've made this diagram. So from this point on, as I said, we don't care about the wiring. We just care about the order in which the variables are read. So let's ignore every other aspect of the program except the order in which the variables are read. So I've made this diagram. So we first read, I mean, by just renaming variables, you can assume that the first time you read them in the order x1 through xn, and then you have some permutation. You read them in a different order. And the question is what to do. So here is a useful theorem that, like Pavel said, that you learn in high school. So Erdős-Szekeres theorem tells you that if you have a sequence of n integers, you can find a monotone subsequence where the length is roughly square root n. So let's think about it for a moment. This is a sequence. The second pass is a sequence of integers. They can be in crazy order. They don't have to be in the order x1 to xn. But what we know is that we can find in this sequence a shorter sequence. So I called it y1 through y square root n that are monotone. And let's assume they are monotone increasing. The decreasing case is you can handle it similarly. And let's do this mental experiment of thinking the ABP that just compute a polynomial in those y variables, the variables that I label y1 through yn, and the field is, let's say the field of rational functions in the y bar element, y complement elements. So you can think of every other variable as just some constants from your field, and the only variables you are left with are y1 through yn. But now, this sequence is monotone, right? It appears here in the same order it appears here. So,
what if it was decreasing?
so even the 2-pass case, I mean, you can think of reading x1 through xn and then reading xn through x1. You can do similar calculations and show that it's not much more powerful. So if it's decreasing, I will just do the same here. But yeah, I mean, we can assume until the end of this talk that every monotone sequence is increasing. That's yeah. So what we have? Okay. So what have we learned? That inside every 2-pass ABPs lies a smaller. Inside a 2-pass with a different order lies a smaller ABP over a square root variables that is actually 2-pass in the same order. No, so y1 through yn are monotonically increasing, right? So let's say this is x1 and then x3 and then x5, which are here. I assume the first read is in the order x1 through xn. I can just assume it by renaming the variables if necessary. So it's the same order in the first time and it's the same order in the second time. And this is great, right? Because we're seeing that same order is good for us. I mean, for every, like I said, for every I in now my indices is 1 from square root n, the evaluated dimension of I and I complement is small, but this dimension is taken over this field. Yeah, this is the tricky thing. But still, what I can do is, okay, so before I describe the algorithm, what I can do now is I can plug in the heating set for 2-pass same order to the y variables, right? I know this is a heating set, so I know there is some assignment that will keep the polynomial non-zero. And then, okay, what progress have I made? I have fewer variables, right? So you can just repeat this argument. So that's the PIT algorithm. You find the monotone subsequence, you plug in the heating set to the variables of y, and now you just recurse with y complement, and each time you plug in a fresh copy of the heating set. So this is like somewhat of a, I want to say technique. It's a technique because it was used once before, right? So when you use something 2 times, it becomes a technique. And when you use it next time, you get to call it a classical technique because. I have this also this amazing diagram, right? You pick the variables, you plug in heating set, you got rid of the variables, right? Because they're not field constant, you have fewer elements, you do it again, and then you just remain with very few variables.
Can you go back?
So yeah, so you have to analyze how much does it cost you. So you have square root n, roughly square root iterations of this thing, and each time you plug n to the log n size heating set, yeah, this log n in the exponent, you can just think of it as, I mean, we have so many worse things going on there in the exponent that this log n is the last thing you should worry about. So overall, you get n to the log n to the power of square root n, which I just wrote as n to the square root n because, yeah, I'm cheating a little bit, but that's okay. So I know that if I only restrict to, yeah, Rafael, you get to see it again. I know if I only restrict to these gray variables. Oh, so there is a heating set for read-once ABPs. This is, many people have done it over and over again. So you can just find the field elements that if you set those variables to these field elements, this polynomial remains non-zero over the field of rational functions in the other variables. But the point is that the restriction is now a non-zero polynomial, and then you just recurse.
So the restrictions, the substitutions are actually rational functions in the main.
No, so you can actually make them field elements because these things always, how these things always work is that you actually get a generator, and then you just need to evaluate the generator in enough points, and if your field is large enough, you can find points from your field.
Think of restricting the other variables to random values when you are on the base.
Okay, yeah, that was a good point. And this is generalizes to k-passes, right? Because you can just apply this thing that lets you find this Erdős-Székely lemma that lets you find the monotone sequence. You can just apply it repeatedly, right? So each time you lose this square root factor, and so your monotone subsequence turns out to be pretty small. That's n to the 1 over 2 to the k roughly. Because, I mean, you first find monotone subsequences in the second thing, and then you further prune it in the third pass, and so on. And yeah, and unfortunately, this is also tight for these kind of arguments. I mean, we know that there are sequences in which you cannot hope for a better thing. But yes, what is this drawing here? It's just there because it's awesome. So that's the size of heating set that you get. This is still not a general case because we sort of assume this k-pass thing, right? We have different order, but it's not the general case. I'm not going to talk a lot about the general case because it's getting pretty technical. So
What might happen is you might read the first variable twice before you read others.
right. Yeah, I have a diagram for this also. Yeah, it's, so let's think of just what happens with read twice, okay? And the first thing that you can do is just apply the Erdős-Székely. Let's assume you've done that. Yeah, so what can happen is you have this green sequence, which is monotone, right? x1, x2, x3, x4. But then you have x1 and x2, and then you move on to x1 and x6, and then you read x3, right? They're sort of interleaving together, those sequences, which is a problem, but it's not a big problem because what we do is we just restrict ourselves more to some like n squared over 3 variables or something like that, and we gain this useful structure that I called, we call in the paper regularly interleaving, but the structure is this. You can partition your variables into sets, x1 through xt, and it looks like that. You first read x1 for the first time, then you read it for the second time, then you're done with x1. Now you move on to x2 and read it for the first time and the second time, and so on until xt. And again, when you run these arguments on these things, everything works. It's you can do this. Somehow it looks like read twice. That you sort of like concatenate those things.
You can combine them into one layer.
Combine with what?
Two occurrences of x1.
No, so the first, x1 is a set. So there is some variable I read here and then I read here. But these are in the same order, so I can combine this.
So there are sets of variables.
Yeah, these are the sets of variables. So I can combine these sets and these sets using the evaluation dimension argument to one read-once ABP. And basically, you can simulate this whole thing by a small read-once ABP. That's the point. And you still have enough variables and those things that you can, you can plug in the heating set and recurse. So that's the read-twice case. And yeah, so that's, as I said, that's enough to carry out these analysis. I mean, you have a set which is not exactly square root n, but square root n over some constant, and still you can compute it with a small read-once ABP. And this, again, generalizes to read k by just, do this repeated application of Erdős-Székely, and you make every pair regularly interleaving, and then you're done. So just to summarize, we got a PIT with running time, roughly this thing. Okay, let's talk for a few minutes about the lower bound. So you can get some weak lower bounds using these arguments. Something is exponential in n over 1 to the 2 to the k. But when you think about it, this was very wasteful, because if you want to prove that the width is large, you don't need, for every layer, the evaluation. I mean, you want to exploit some weakness of a read k thing. And we somehow assume that every layer has a small evaluation dimension, but it's enough to find one layer where the evaluation dimension is large. So, I mean, what we want to show is that if f is computed by a read k oblivious ABP, we can find some prefix, 1 through I, such the evaluation dimension is at most w to the 2 to the k. Okay, this is not quite true, but it is also not a very big lie. This is very close to being true. So here's the claim that I want to show, that I can fix a very small number of variables, something like n over 10, and then I can partition the remaining variables to some subset S and T, which are pretty large. Each of them is at least n over k to the k, and the evaluation dimension will be small. So this is, again, this is not exactly what I said earlier, because now I'm fixing these variables, and I want this robustness property that evaluation dimension, that S and T are large, but the evaluation dimension is small. So how do we do that? Well, you have this long program. You can just partition it into blocks, in the contiguous blocks. R is the number of blocks. We will set it in a moment. And so you can match each variable with in which blocks its occurrences occur. And so there are R choose k sets of k blocks among the R blocks, and just by averaging argument, you know that there exists a set of k blocks that contains all the reads of n. N is the number of variables, n over these variables, right? This is always a little bit confusing for me, at least. Even when I prepared the slides, I had to think why this claim is true. But it is true because you match each variable with the set of k blocks where it occurs, and then you just do this averaging. So let's say these are these blocks. And now I want to arbitrarily fix all the other variables in this block. So these n over r choose k variables are s, and any other variable that happens to fall on this block, I just fix it to 0 or to random thing, it doesn't matter, arbitrarily fix them. And t will be everything else, everything that remains. And now, again, I have this structure of at most k alternation between S and T, and I can use the exact same argument in order to bound the evaluation dimension. So it just remains to see what R should be. So if I pick R to be something like 10k squared, I get that the number of variables I have to fix is at most n over 10. And S is large enough and T is large enough, as everything is cool. I don't know, by the way, I have lost all sense of time. Do I have to finish like half an hour ago? Or, okay. Oh, that's great. That's great. Yeah, so I mean, you can just, this is a calculation that I didn't write on the slides, but you can just count how many variables can occur in each block, and you can see that the number of variables you fix is at most n over 10. So why is it so small? So all that is left is to find some explicit polynomial that, you know, whenever you partition S and T, the evaluation dimension will be large. So it will be at something like 2 to the minimum of S and T. So it can be, I mean, the number of, if it's a multilinear polynomial, the number of rows of this matrix is 2 to the S, and the number of columns is 2 to the T. So this is like the highest it can be. And you want to find something, so we know how to find things. We want to find something that remains pretty high rank even after you fix n over 10 variables. This is not hard. All right, so let's summarize what we've seen. We had this exponential over bound for some polynomial in VP. We show that you cannot compute it in a read K oblivious ABP unless the width is really large. We also have this PIT algorithm with where the running time is slightly subexponential. I mean, it's not so it's non-trivial, and there are many open problems. I've just listed a few. Of course, the most urgent thing is to come up with a faster algorithm. So you should run out and do it now because it's urgent. It will also be nice to have this black box instead of what I call gray box, to have absolutely no dependence on the order. Because, I mean, if you just try to generalize this and sort of guess these sets and do the calculation, you will see that you have to do exponentially many guesses, and it doesn't get you anything which is subexponential. So it would be nice to find some different argument that can bypass this thing and get you to black box PIT. With regards to lower bounds, it would be nice to have some sort of hierarchy to show a polynomial that you can compute in read k plus 1 and not in read k, an example. In the Boolean model, we do know how to do it. Here we don't know. So we can sort of separate something like read k to the k versus read k. But we do not know how to do k plus 1 or something polynomial in k versus read k. This will be very nice. Yeah, and there is this word oblivious that I keep using. And it will be nice to have something that doesn't require this. This is open even for k equals 1. When k equals, I mean, so what do I mean by non-oblivious? I mean that on every path, you see every variable at most k times. This is actually the natural Boolean model, and this is what they prove lower bounds for. In the algebraic model, we don't know even how to do it when k equals 1. When you have this multilinear for ABP that you, on every path you encounter each variable at most 1. And finally, no, we keep saying that maybe there are connections to Boolean branching program, and maybe they can learn from us, or maybe we can learn from them. So we keep saying that, and maybe it's true. Maybe we can use some of these ideas to get pseudo-random generator with sublinear seed length for read K Boolean branching program. There, I guess you would need obliviousness, because also in the PRG for read-once we require obliviousness, but yeah, you can wonder whether it's possible. So yeah, that's it. Thank you.